Hi, everyone, and thank you for attending. Hi, my name is Corey Prowse, and I've been an engineer in the industry for 25 years. I consider myself pretty lucky that I spend at least half my time doing engineering while I manage globally the technology department of Citi investment strategies from London. Now, I love what I do, as every day I get to wake up and solve interesting engineering problems that involve massive data sets, which are fed through algorithms requiring extreme precision. All of this served up to our users who of course expect fast response times from potentially many queries running in parallel. My teams develop and operate these systems with an Agile and DevOps mindset, meaning we work daily in close collaboration with our users to iterate on our work and deliver multiple times a day to production. On top of that, Citigroup has a department devoted to developer experience to ensure we are empowered with the tools and technologies to achieve these ambitions. Now, quite likely, a lot of what I just described is similar to your own work environment today. If not, well, there is a URL there on the right side of the screen where you are welcome to apply for open roles at Citi, as we're always hiring. Now, in this presentation, I'm going to walk through an interesting microservice that we have at Citi that evolved from an existing solution that we were using Couchbase for. So, of course, we use Couchbase traditionally in the terms of like create, retrieve, update, delete, the old CRUD pattern. But we've also evolved what is essentially a time series version of a database living within Couchbase that can scale up to billions of data points spanning more than 20 years. So I'm going to begin by describing the problem, and I'll move through how we've made it efficient and reliable means of providing this data. So first, the problem. In essence, what I'm going to describe is a market data system. Now, the concept of a market data system usually refers to a computer system which receives and provides information on financial markets. So an example of that might be stocks that could tick possibly thousands of times a second or rarely at all. Now, this can add up to billions of data points when you consider that this goes back over 20 years. So this data in its raw form isn't always what we really care about. Usually we feed this to an algorithm, which then provides yet another layer of data that we then lay over that timeline. And sometimes that layer again is fed into further algorithms to produce more layers, or potentially in real time stream to other systems, which then reflect them back to us, which provide an extra dimension yet again. So there's a real-time event-driven element in what is essentially a massive time series. Now, the kind of queries which our users do, first of all, there's the simple one. You can ask for, give me the exact point in time in the past, give me the value that something was. But beyond that, they might ask for a block of time. So give me all of the data from the beginning of this point to the end of another point. And then lastly, a variation on that, perhaps we want to walk the timeline in a pattern, which could involve jumping forwards and backwards in time to collect the data points that are required for an algorithm. Now, those last two there, they could potentially be many megabytes or gigabytes in size, the data that the client requires. Now, we can't hold all of that in memory at once. And sometimes we need to actually perform calculations on the fly because the actual values we're providing to our clients aren't the raw values. We don't store them anywhere. We need to provide some enrichment as the data is fed to the clients. Now, as I mentioned before, we need to do all of this with thousands of concurrent requests and provide them in a response time of milliseconds to our clients. At certain times of day, these systems can receive massive bursts in traffic. At other times of day, it might be quite idle. But this is the kind of system where it provides an interesting engineering problem where they're all common engineering concepts applied in an interesting way. So the first thing I'll talk about is the data storage, the actual data that is put into Couchbase. Now, to start with, we can't store every single data point as a separate document. That would be billions of documents stored in Couchbase. And so instead of storing each individual point, we store sections of the timeline. So in this example here, I've given that we are storing them in 30 minutes of buckets of time. So if I want to find a particular point in the past, I just figure out which half-hour bucket I need to load, and then I find the time within that bucket. So in this case, you've got 10:23 and 16 seconds and 123 milliseconds. So from that, I'm going to load the 10 o'clock bucket. And then from within that bucket, there is a timeline which I'll traverse to find that point in time and return the data that the query was requiring. To push this point a little bit further, here's the a first cut at what we might do for providing this data in a JSON document. So on the right side of the screen there, I'll draw your attention to the timeline field in the JSON. Note that it's just an array. It's just an array of the data points sorted in time order. But I mentioned before that potentially some of these items can occur thousands of times a second. So if you extrapolate that over a half-hour period, that's a massive amount of data in some cases, and it won't fit within the 20 meg limit for a single JSON document stored in Couchbase. So to overcome that, you'll see the next field down there, overflow, and that provides further document identifiers for those extra documents to traverse after this one for the overflow information that couldn't fit in that original 20 meg limit. Now, we aren't just storing time series here. We're also able to provide extra dimensions to the data. So we might, for example, have a field like foo, which has other fields that are actually fed into indices that can be used in nickel queries to provide yet further insight into this data set. But simplistically, most of the time, if we're just traversing the timeline, we just do a GET request. Now, to do a GET request, again, we want to know what document we want to get. So we want to know what the half-hour document period is. Well, if you look at the document ID at the top right there, again, just a simple example, you've got the type of data, followed by the identifier for that type of data. And then lastly, the start time for that half-hour bucket. With that, we can do a simple GET request to Couchbase. We bypass needing to go through the query service, nickel, indices, and all that, and go straight to the document to fetch it, and we can provide that to the clients. But we're not done yet. In terms of the JSON structure, as I mentioned, there are possibly hundreds of thousands of data points within a half-hour period. That can really scale up. And if you do something inefficient hundreds of thousands of times, of course, it's going to have an impact. And so we needed to look into the format of how we store those individual data points. So looking at that again, this is just a first cut. Looking at the right side of the screen, you'll see here is just the portion of that JSON document for the timeline. It's an array of values. So as a first cut, let's say we use JSON objects. So there is a field in each object, which is for the time that it occurred. And then just to keep it simple, just a value, which in this case is just a number. Now, straight away, this is inefficient because storing it as a string that requires some parsing means that every time you load that document, you're going to be parsing possibly hundreds of thousands of dates into a date object. So we're talking here about converting a date string, an ISO date string, into a POJO, plain old Java object. And that means we're going to have to, like behind the scenes, of course, we didn't write the code, but within the JDK libraries, it's going to parse that into tokens, figure out the year, the month, the date, the hours, the minutes, the seconds, do lots of maths to figure out essentially what point in time it is to then store it inside a Java time date object. These small inefficiencies add up. Beyond that, though, there's a massive amount of wasted time. If we want to load a half-hour bucket and all we really care about is that first item in the bucket, we've just gone and parsed possibly hundreds of thousands of data points when all we really cared about was the first one. So to avoid that, we don't store date time strings. We store Unix epoch time. So basically the number of milliseconds since 1st of January, 1970, which is actually underneath the hood what the date time object stores. Now this avoids massive amounts of CPU because parsing a date string, like I mentioned, there's tokenization, converting the hours, minutes, and all that to a magic number at the end. Why don't we just give it the number straight up front? But more importantly, this also has a massive reduction in the amount of RAM required. So if you look at a single numeric stored in memory, a long, that's 8 bytes in Java. Compare that to a string. Storing that string, it's 2 bytes per character, which could be something like 40 bytes for a simple ISO date string. That's an 80% reduction in RAM required to store that in memory. And we're just talking about loading that string as the JSON string from Couchbase into memory. Similar improvements can be made for other fields. So I'm just showing this as an example for a datetime string. But if you're quite cognizant in terms of what effort your JSON library, such as Jackson, is doing to parse these strings into POJOs, then it can really add up when you're doing it hundreds of thousands of times. But we can still do better because the size of the document that we're storing in Couchbase is a string. And so you can see that there's a repetitive nature here of the time field name and the value field name repeated throughout. And that reduces the number of items that we can store in a given bucket, considering, remember again, the 20 meg limit of the documents. So to solve that problem and scale up the JSON performance even further, we can store it in an array. So you see at the bottom right of the screen there, the new format that we're using. So now the timeline field is a 2-dimensional array. It's an array of arrays that basically have the time as the first item in the array and the value as the second item in the array. Now this has increased our storage, as mentioned. There's much more we can store in a single document because we're not repeating those time and value fields, but it also means that faster parsing, so more efficient time as well. Now to avoid this kind of complexity that's now being used to store the data in the database, to avoid it bleeding back into your code base, You can use features in certain JSON libraries that allow for it to be handled at the time of deserialization or unmarshalling. Now with Java Jackson, the popular library for parsing JSON, you can use, as you see the bottom left there, some annotations to say that the shape of this document is an array, and then provide an array of the names of the fields in terms of the indices of the array. Now, of course, this means you can't go and look at the document in the Couchbase and have a easy go at looking at understanding it. But it's rare that anyone really wants to go and look at a document with 100,000 data points. So it actually adds up to a massive win. It's a balance of practicality that I feel is a good win. So again, this provides a really nice way to scale up the storage of pretty much any JSON document if you're willing to pay the extra complexity factor of your data in the database being a little less friendly. Now, again, if you did want to write an index on this and do nickel queries on it, you can. It just means that your nickel queries and your indices will be referring to array indexes, which aren't as friendly as potentially referring to it by name, such as time and value. Again, it's a balance in terms of where you want your architecture to be. So I've gone through what the problem is. I've described how we store the data and how we've improved the JSON structure. The last factor in this is how we allow for a massive amount of parallel queries to occur. So just to revisit the problem a little bit, if we had a lot of users all requesting possibly many years of data, that can add up in many ways. First of all, I'm going to talk about the time performance. As I mentioned, we're storing all of these items in separate buckets of half-hour time periods. So if we were to go and fetch every single bucket to then concatenate together into one big massive response before we start streaming it, then there will be a massive delay from first byte to the user. So we don't want our users to sit there wondering why the system isn't performing. So we want to start sending that as soon as possible. But beyond that, even more, we won't be able to scale out to a large number of users all requesting data at once, because if they all needed to load up a large amount of memory to then start streaming the response, then we wouldn't be able to scale out as much. And so what we do is we avoid that. We want to reduce the amount of memory so that we can increase the number of users that are all requesting this data in parallel, which looks a bit like this. So what we do is we do a query to the database using the new reactive streams that you can use in the SDK 3 version of the Couchbase libraries. And from there, we basically feed that TCP stream to the users with just enough data to keep the TCP stream alive. Now, this has, of course, a massive reduction in RAM, which means we can support a larger number of users all in parallel because there's extra RAM free to support the buffer of information that's feeding their separate TCP streams. But more importantly, it improves that time to first byte. So users do not see a delay. They immediately start to see data streaming. It gets past that classic computer science problem of a fast producer and a slow consumer, where essentially what we found in production is that the speed in which we can send the data to our users is way faster than they can actually consume and process it themselves. So we need a mechanism to slow this down. And that's pretty much built into TCP with built-in back pressure. Now, on the back of that, what we've done is we have used a technology called Reactive Streams. So Reactive Streams began back in 2013 and was finalized in 2015. And in short, it's an initiative to provide a standard for asynchronous stream processing with non-blocking back pressure, which is exactly what I mentioned before with TCP. So this maps perfectly in terms of concepts on top of TCP. Now, I'm not going to dive too deep into the Reactive Streams and what it is, but if you do want to know more, there's a URL there for the website, which is the first point of contact. However, if you're on Java, it's been there since Java 9 in the Java util concurrent flow package. So you may already be using it behind the scenes today. And this also touches on another architecture concept called reactive. Reactive architectures are, again, a much deeper concept, but this is kind of like one of those elements in the reactive architecture. And specifically, we're talking here about the item at the bottom there in the diagram called message driven. And it allows for an architecture that reacts to events around it. And it really simplifies a lot of these problems where you're streaming data to the users. So I'm just going to give a bit more background in terms of like how this works before I dive into the end result of how this was all packaged together. So in terms of functional reactive programming, which is what we're really talking about here with reactive streams, a common means of communicating what goes on in these streams is a marble diagram. And I've got an example here. So first of all, I'll draw attention to the black line that goes horizontally across with an arrow at the end. That shows the progression of time. Because again, we're talking about asynchronous events that are being streamed across to the users. The individual circles there, otherwise known as marbles, represent an event that occurred. So here they're saying it could be a click event from a mouse. But for us, it's most likely a packet that arrived from Couchbase with data that we want to stream to the client. Now, there's only two ways in which one of these streams can terminate. First off, if something goes wrong, it'll terminate with an error. That's what the red cross means. And then second to that, if it completes normally because the data has completed, then it finishes with a completion. Now, it's only going to terminate with either an error or a completion. It won't terminate and error both at the same time. It'll only just be one of those. But just to show all the elements on one screen, this is a marble diagram. So now I'll just walk through some of the ways you might kind of think in a functionally reactive programming way. So first up, the venerable map from functional programming. When we want to apply a function to another value and transform it. So in this case, we've got a simple stream of numbers, 1, 2, and 3, and we're going to apply a function to it, which multiplies all of the elements by 10. So 1 goes to 10, 2 goes to 20, 3 goes to 30. But note here that 1 and 2 are close together and the 3 is further along. Again, it's showing that the elements are traversing in a time-based system. And here you can see that the 3 and the 30 line up further apart in the same distance as the 2 and the 3. All right, so let's build upon this a little bit more. And here what we've got is another function, which instead of producing a single element emitted to downstream, it could be emitting multiple. So here we've got a bit of pseudocode that says a single circle is emitting 2 diamonds downstream. So again, pretty straightforward. A single red circle produces 2 red diamonds, and then a green circle produces 2 green diamonds. But note that the blue circle, even though it's emitting 2 blue diamonds, doesn't start emitting downstream until green has finished emitting its elements downstream. Because another important element in the reactive streams is that the element ordering is preserved. So it's a nice programming model to do, again, all this kind of data streaming. I'll just show one more, and here we are, is a mechanism that can be used by the subscriber downstream to control the life cycle of the stream. So here it's take while. Essentially, we're only going to accept elements from upstream while that condition is met. In this case, that the elements are less than 5. So again, 1 is received, 3 is received, but when the 6 is received, well, it's not, because it isn't less than 5. And so that's where downstream cancels the stream and the stream completes at that point. So you can see that there's a lot of power here and very little code in what you can do. In fact, there's even more elements that you can use, such as throttling, so that upstream can only send elements up to a certain speed, allowing the server to control the speed of the transmission. Or you could have a fan out, like a broadcast of elements to parallel streams and do calculations in parallel before then potentially merging them back into another stream and sending down to the client. So there's a lot of real-time asynchronous calculations that can be done with this. It's very, very powerful. We use this quite a lot for how we do calculations on the fly, perhaps enrichment of data from other systems, or some algorithm that requires some parallelism in it. All right, so let's start talking about how this actually translates into code. So in terms of streaming documents, and I'm going to keep this in the simple scenario of let's just provide a sequential block of time. So we're not doing that pattern I mentioned before. We might be jumping forward and backwards in time and cherry picking items, although it would just be a further extension of this concept you see here. Now on the right side of the screen there, I've just used some pseudocode. It's no actual language, keeping it agnostic, but I've got an iterator. And that iterator essentially will produce the identities of the time for each of the buckets. So it starts with start time until it reaches end time, and it just keeps adding the number of milliseconds per bucket, which would be how many milliseconds are in half an hour. So this can be generating the identities that we go and load from Couchbase. And again, we're not talking about nickel here, we're talking about simple GET requests. Now, this is where we bring it all together into the final picture. So here at the top of the right screen there, you see that there's a source, and it's using that document ID generator I mentioned before. So essentially it's generating the time for 10 o'clock, 10:30, 11 o'clock, 11:30, and then converting that into the GET request to Couchbase to fetch each individual document. As you can see, the async collection.get. And then immediately after that, it parses that document. As mentioned, we've got an efficient mechanism for storage, retrieval, and parsing of that JSON document now. And then the next step, that's using flat map concat, very similar to the method I showed before where a single circle generated 2 diamonds. Well, in this case, we're saying to generate a stream of elements based on the timeline within the document. So now we're essentially sending each individual data point down to the client. But again, if we wanted to limit from a start to a finish, well, then we can use drop while or elements like that to say, ignore everything until we reach the start time, and then start allowing those elements downstream. And then to complete it when the user wanted it to end, all we use is take while. And here we're saying essentially, give me all the elements up until the end time, and that will cause the stream to end. Now, again, this could feed into another part of a stream which does further enrichment, further algorithmic complexity, however you want to that is essentially a simple mechanism to provide a large scale fetching of data. Now, the system I'm talking about here, like I mentioned, it does a massive amount of queries in parallel. It's used with possibly definitely over 100,000 an hour, sometimes over 1 million a day queries are being fired through these kind of queries. And again, this can happen at certain times of day, which the system can be quite busy, such as market open and market close. And we found it to perform extremely well under pressure. Because one of the concepts of this is it's working as fast as the system allows. So you can see here, generating a document ID is pretty much free. Asking Couchbase for a get, that scales really well as well. But if for some reason we're having a lot of queries in parallel, the whole system slows down to as fast as it's allowed to be. Now that could be due to the load on Couchbase, but quite frequently it's due to the load on our microservice, which is performing extra calculations or fetching extra data from other systems to enrich it with. So again, it's operating as fast as all the external systems allow it to operate. It's a very simple concept to use, and it's very powerful for us to use in terms of the way that we provide data to our clients. So again, I've gone through this. I've described the problem as being a massive billion data set, how it's being stored to make sure that it's stored in an efficient mechanism for lookup, and then how we ensure that the data structures that we store there are quite efficient, and not just in storage, but how we retrieve and parse it, and then how we scale up in a massive amount of parallel queries. I really enjoy this kind of stuff. It really does exercise the low-level engineering aspects of what we do every day as engineers, and I find it quite fun to talk about. So thank you very much for being here today, and I appreciated the opportunity to talk.